Graphs. Not the bar chart kind, the other kind. The ones that sneak their way into social networks, GPS apps, neural networks, and yes, your IB AI exam as well. Let's take a look at what actually makes them so powerful. Frank Harari, a famous mathematician, once said, "A graph is worth 1,000 words." And that's because graphs don't just store information, they actually show relationships. Whether it's cities or roads, friends and followers on something like social media, graphs can tell a story. But what is graph theory? Graph theory is the study of things modeled as vertices and how they connect to other things through edges. Or, more formally, graph theory is the study of graphs, which are structures for modeling systems, which have pairwise object relationships. But more than that, it's a kind of way of thinking of reducing messy real-world systems into something a lot more elegant. And as a result, graphs can show up in computer science, logistics, biology, artificial intelligence, and so many other fields. Here they are in your IB AIHL syllabus, opening a door to topics like optimization, shortest paths, and even page ranking. But what are graphs? Let's break it down. So a vertex is just a point, person, a place, something which you care about and you want to represent a relationship with. Edges are what form these relationships, as they're the connections between these vertices. And together, the sum of these two sets of vertices and edges form a graph. Think of something like a subway map. Stations can be vertices, and the tracks connecting them are the edges. And suddenly you have an entire railway system being modeled by a graph. On the right, there's a basic graph. Nothing fancy, just 3 vertices and edges connecting them. But already it has connections. If we say each node is a computer and each edge is a direct cable, then this graph can become a network topology. Or if these nodes were cities and the edges were roads, then we already have a transport map. The same graph can have different meanings depending on the context. Graphs can have different types of personalities though. A simple graph is just clean connections, no repetitions. That is, at most one edge between each pair of vertices. A directed graph means that edges have a direction, kind of like one-way streets. And weighted graphs, edges carry a weight, like distances or costs. This is where graphs become more than just diagrams. They become tools. Because say you need to find the shortest route, you'll need to find weights. Need a model of flow of information, you'll need direction. You've also got multi-graphs, where multiple edges can exist between the same 2 vertices. Connected graphs mean that every vertex is reachable in some way from any other vertex. And you have disconnected graphs, where some parts just don't talk to each other. Next, we got to talk about degrees of vertices. How connected is it? Well, that's what we call the degree. For an undirected graph, degree is just the number of edges that are connected to it. Whereas in directed graphs, we split it in 2. We have the in degree for edges coming in, and out degree for ones going out. Simple, but super powerful. Degree tells us the importance. If you have a node, for example, which has a very high degree, that node's probably pretty central, popular, maybe like a main train station. A low degree, maybe it's more of an outlier, or isolated. This will form our understanding of concepts later on, such as page ranking. Looking at the graph above, just looking at D, you can see it has the edges DA, DB, and DE, meaning that it has a degree of 3, as it has 3 edges incident on it. For directed graph, this becomes a little bit more complicated. Looking at B, you can see that it has an in degree of 2, because we have AB and EB, but it also has an out degree of 2 because it has BD and BC. Sometimes it can be helpful to represent a graph with numbers instead of drawings. That's where an adjacency matrix comes in. Each row and column is a vertex. If there's a connection, we put a 1. If there's not, it's a 0. It's like encoding the structure of the graph into data, and it's super helpful when writing algorithms. If we look at our example here, you can see AA is 0. That's reflected as there's no loop from A to A on the graph. A to B, there's a 1, because we have this edge here. A to C, this edge. B to C, we have this edge. And notice for undirected graphs that there's a line of symmetry across the diagonal of the matrix. This makes intuitive sense, as if you have a connection, say, A to B in an undirected graph, B must also be connected to A. C to A means A must be connected to C. What about directed graphs? Same idea, but directions matter. A 1 from row A to column B means there's an edge from A to B, not necessarily the other way around, as we saw with undirected graphs. This is useful for modeling things like who follows whom on social media. In this case, you can see A is connected to B, represented by this edge. It's also connected to C, represented by this edge. But you can see B is not connected to A, and C is not connected to A, which is reflected in the graph. So next time you see a cluster of dots and lines, just remember it's not just a diagram. It's a system, it's a model, a graph, and it might just be smarter than it looks. Stay tuned for part 2, where we'll explore things like Prim's algorithm and Kruskal's algorithm. And if this helped make graph theory click, then please consider giving it a like, a share, or even just thinking about graphs a little differently.